All right, so a Gaussian cube contains a charge q. I'm going to draw it out like this. Oh, bad cube, whatever. All right, and so we have a charge q on the inside. First part of the question. If q is at the center of this cube, what is the flux through each face? Well, Gauss's law states that the total flux through any surface is equal to the charge over epsilon naught. Total charge enclosed over epsilon naught. The total charge enclosed is q. And since it's directly at the center, it's going to be symmetric at every single face on this cube. Since a cube has 6 faces, the flux through any given face is going to be q over 6 epsilon naught. Alright, so the second part of this question is, if q is free to be placed anywhere throughout the cube, what is the maximum value the flux can take through any given face? So, if it's at the center, we established that the flux through one face is going to be q over 6 epsilon naught, regardless of what face we're looking at, because it's symmetric. If I took q and I took it closer to the front face, the flux through that face is going to be greater. The reason is because q, as an electric field, the electric field of q is going to have field lines, right? And the closer you are to the center, the more dense the field lines become. So the closer a face is to a charge, the more dense the field lines will get. If I bring q right up to the edge, right up to the edge of the cube, exactly half of its field lines will be going through. So the maximum value of flux that can happen through one face is going to be q over 2 epsilon naught. Alright, so for this problem I have a wedge. And this wedge has an electric field kind of permeating through it along the x direction. There's no charges inside. This wedge is at an angle of 60 degrees on the upper part. It has a height of 10 centimeters and it has a depth, a width of 30 centimeters. And the question is, what is the flux through the back face? So this part right here, what is the flux through this back face? And the question really is, it's really going to be the electric field dotted with the area times the area vector. The area vector is essentially a unit vector pointing perpendicular to the face and to the outside. So this n hat, this unit vector, is going to point out toward the back. Since the electric field is pointing in the opposite direction, this is going to be the magnitude of the electric field, the area of this face, and the cosine of the angle between those two vectors, which is going to be 180. This just means we're going to have a -1 in front of it. The area of this face is going to be 10 centimeters times 30 centimeters, which is going to be 0.3 times 0.1 meters squared, or 0.03 meters squared. So we end up getting -5.0 times 0.03, which is going to be -0.15 Newton meters squared per coulomb. Alright, so for the second part of this question, we're trying to find the flux through this face, this slanted face. Alright, and again, our flux is going to be E dot A n hat, essentially. The area of this face is going to be a little bit more complicated because we don't know the length of this hypotenuse right here. But we can figure this out. If this length, I'm going to call it d, d cosine of 60 is going to equal our 10 centimeters. Cosine of 60 is just going to be 1/2. So d is just going to be 20 centimeters. Okay? So the total area of this is going to be 0.06 meters squared. All right? And as always, E is going to be 5.0 newtons per coulomb. And the angle between an electric field vector, and the n hat is actually going to be the same angle here, 60 degrees. So it's going to be a times e times cosine of 60, which is 1/2. 5.0 times 0.06 times 0.5. Well, this is just going to be 0.03 again, which is just going to be 0.15 Newton meters squared per coulomb. And for the last part of this problem, it's going to be a really easy one. What's the total net flux for this entire volume? Well, we just add up the flux for these two faces. For the bottom face, this face right here, and for these side triangular faces, there is going to be no flux because the angle between the normal for each of these faces and the electric field is going to be 90 degrees, which essentially means they're perpendicular and the dot product is going to be 0. So in that sense, we just add the flux through the back face and through the front face. And this is quite nice because since it's negative 0.15 Newton meters squared per coulomb and 0.15 Newton meters squared per coulomb, the total sum is just going to be 0. There is no flux throughout the surface, which makes sense according to Gauss's law because there is no charge inside.